I'll download the handout for myself just to, in case I need it, I'll put it out of the way. Just put it on my other screen so I can go back to it if I want to. You can, of course, do the same thing. Have the handout in front of you. Full screen. And I like my pointer. So, cosmic microwave background radiation. It's a whole mouthful, but it is absolutely essential to discuss it, and because it has been the vehicle, primary vehicle, observational vehicle to bring cosmology to where it is now. There's an image which you may have seen before. It's if you look it up, see a cosmic microwave background. It has different abbreviations. CMB, I think, is the most common one. CMBR. You'll get an image like that, and that's clearly an all-sky image, and I'll discuss that. But as I mentioned, historically we were really short in observations, and but now the tables have turned quite significantly, and we now have a huge amount of information, especially from this radiation, which drives modern cosmology. And it is amazing how many conclusions we can derive from observing that radiation. Of course, with increasing precision when the technology improves. You know that I always like to put things in a historical perspective. But in this case, it's really important in my view, because there is a lot of misunderstanding today, even among scientists, about who were really the ones that we should celebrate for the discovery of this radiation. And there's no other way than start with the guy called Ralph Alpher. He was a student of George Gamow in one of the universities in Eastern United States. I have links in the handout, and I'll definitely recommend that you follow those if you're interested. He wrote his doctoral thesis on the formation of primordial elements, and this is something that we will come back into. I have in the past discussed what we call nucleosynthesis or nucleogenesis. This is the question, where do all the elements come from? In the stellar evolution discussion, I've referred to that. But now what we're going to talk, and this is a modern topic, but he started his research on asking himself, how did the elements form in the very early stage of the universe? And which were the first elements? It was fairly obvious that was hydrogen and helium, because these are the simple elements in the simplest elements in the periodic table. So he was, and that's where the word primordial comes from. So he was thinking about the expanding universe, and what Lemaitre had suggested, that it had started as a primeval atom. I think that was the words that Lemaitre used. I talked about it last week. And that we are now in the ashes of this fireworks that happened. Was his way of describing the Big Bang. And this is in 1948, so that's 20 years later, that he started to think about the formation of the Earth's first elements in the universe, in a very hot, dense universe. And while he was writing this, and he published this, he came to the idea that there could be some sort of radiation, because, and I'll come back to that in the next few slides, but if you think about the sun as a star, which I've discussed in the first course, we have it looks like a very sharp edge, which you call the photosphere. If you look through safety goggles with to the sun, you will see a very sharp disk. That edge is just it's not a physical edge at all. And I explained this in the first course, but that's a long time ago, so I'll repeat it. But I'm making up that reference because we're going to the cosmic microwave background. But if a plasma is very hot, then electrons are blocking photons. Photons scatter off electrons on free electrons. I talked about plasma, that's electrons are stripped away from the nucleus. It's mostly hydrogen anyway, even in stars today, like our sun. So these are individual protons and individual electrons that are floating around. And these electrons, because they're free, they block photons in electromagnetic radiation, because there's a form of scattering that basically prevents these protons to travel very far. They will immediately scatter off the next nearby electron, and that keeps happening all the time. And this is why the sun, and then other stars below the photosphere are opaque for light. Light can't come out. But at some point, the temperature decreases as you go further out from the center of the star. And then at the critical temperature, these electrons can bind with the hydrogen nuclei, with the protons, and then the photons can come out. So this opaqueness of the star, suddenly at a certain temperature, which is a certain distance from the center, suddenly the light can come out. So this is why we see this photosphere. And Alpha thought about this in terms of the whole universe in its very early stage, expanding, extremely hot, extremely dense, but then expanding means lowering in temperature. And he thought, well, hey, there should be a particular temperature, which means an age of the universe after the Big Bang, where electrons would bind with protons, form hydrogen, the atom hydrogen, and then the universe would become transparent. And before that time, when the temperature was too high, light could not come out of the very dense universe. This really was the start of theoretical thinking of what we now call the cosmic microwave background. And he should deserve all the credit for that. Very shortly after, he worked with a friend of him, Robert Herman, it's the guy at the bottom photo, and they published and made a publication. They wrote a paper about this idea that there could be a moment in the history of the universe that it suddenly became transparent, the universe, and then the first light, literally, the first light came out. And what they imagined, because we know and they knew that the universe was expanding, that and meaning lowering in temperature as well, that light would have been traveling for all these billions of years, had been severely redshifted because of the expansion of the universe. And they could estimate that would be something like in the microwave range, radiation. This really is the whole concept of what we now call cosmic microwave background. But this was in the late 1940s. And there were very few people who paid attention to it. And then in the 60s, it was almost, well, at least 10, maybe a decade, maybe a little bit more than a decade later, this idea was rediscovered by several people. One of them notably was the astrophysicist that you see here, Jakov Zeldovich. And another guy was in Princeton, in the Eastern United States, Robert Dickey, that's this guy here, who ran a group. He was a cosmologist or a theoretical physicist mostly. He did lots of things, but at some point he got interested in cosmology and in the early universe. And he was expert in radiometry, in building horn-like telescopes for radiation, for microwave radiation, basically. That's called the Dickey telescope. And he was thinking theoretically along those same lines, but this was a rediscovery from what Alpher and Herman had been discussing in their paper almost, well, at least more than a decade earlier. And then I mention him now, Jim Peebles here, this guy, in his younger days. He was a collaborator of Dickey in this group. And he published in 1965 a paper where he suggested that this radiation should be observable. We should be able to find it, but then in all directions. And it would be a microwave phenomenon, microwave wavelength. And at that time, Dickey's group, because he had already built those radiometers, he decided to build one for himself, specifically to try to find that radiation. And then what happened is that 6 years before, one of those Dickey radiometers that Dickey himself had designed had been built for Bell Telephone Labs. And they were very nearby Princeton in a place called Crawford Hill. And here you see that horn-like telescope. And these guys, Penzias and Wilson, they worked with that antenna. They worked for Bell Telephone Labs. They were not interested in cosmology or something, not in any specific way. They were just doing their job for Bell Telephone. The reason for this research with this radiometer was satellite communication. There was in a very early stage, satellites in the 1960s. And also some radio astronomy. I don't know the clear details, but that was their line of work. They were intelligent guys. They were really on the ball, but they had no connection with cosmology. And very famously, they studied radiation that they observed with that telescope, which came from space. And they found a background noise, as they call it, which had a certain temperature. You can define antenna temperature, the temperature of the radiation in degrees Kelvin. It was a very low temperature, and it was a consistent noise, like a hum on the background. And they had all kinds of ideas what it might be, even as mundane, as pigeon poo, which was the pigeon there. They were nesting in that horn antenna all the time. So they cleaned that out, and it's a very interesting, kind of a funny story. So that was a problem which they could not solve, and no matter in which direction they pointed the antenna, they still had that noise all the time. And at some point, let me stay with this slide. At some point, they maybe published something about it, or word got out. And it was almost a stone throw from where Robert Dickey was having his group in Princeton. And Dickey got, this guy here, he got word of this discovery. It wasn't even a discovery, it was just a problem which they observed, that background noise, that they were having that problem. And then Dickey famously said, "We've been scooped, because they have discovered what we were setting out to do ourselves." This is the history of how it was discovered. And then the very unfair aspect of this is that in 1978, the Nobel Prize for Physics went to those two guys, Penzias and Wilson, for that discovery. This, in my view, and I'm certainly not alone, this is one of the worst decisions that the Nobel Committee has made. They have received a lot of criticism about appointments, and they never can get it right. We need to be realistic about that. But, and I have a link in the handout to that discussion, and you can see a whole list of contentious decisions that were made over the years by the Nobel Committee. But the point is that because Nobel Prizes can only be given out to people who are still alive, cannot be posthumely, that's just a rule. But I've looked up the date that people passed away who I've mentioned before, and they all were alive and kicking in 1978. So why did they completely bypass the people who, the actual cosmologists, you would say, who had the theoretical insight that there should be something like this, and then Dickey, who had just decided to build a specific radiometer to hunt for that radiation. I think it's very unfair that Penzias and Wilson got the Nobel Prize, and consequently they become very famous. They are the ones who discovered cosmic microwave background. So the reason that I give you this history is to somehow give some counterweight to that whole myth of Penzias and Wilson. These are nice guys, they're intelligent guys for sure, but they had nothing to do with cosmology. It was a completely serendipitous discovery that they made. They were actually annoyed. So yeah, that's the story of how this was rewarded. Alpha and Herman, they got very high prizes within the United States, other prizes, when it was realized how important their initial research had been. Peebles, I mentioned before, the collaborator of Dickey in the group, he got a shared Nobel Prize in 2019. That was a much later date. He got that for his general contributions to theoretical physics in relation to cosmology or something like that. So that was very late after that, after the original discovery. He shared this, by the way, with two other people who were the first to observe an exoplanet. We've talked about this in the exoplanet course or lecture, and this is the second course. Quaylos or something, a very strange name, starts with a Q, and another guy. It's not relevant now, but this was a shared Nobel Prize between three people, two for the exoplanet discovery, and Peebles fairly late for his contributions to cosmology in the context of the cosmic microwave background. But these people should really have been honored with for the work that they have been doing, the foundational work that they have been doing for this discovery. Anyway, just wanted to make that point. So what is happening, and this is what I explained in terms of the sun. So if you have a hot plasma above a certain temperature that electrons cannot bind, the electrons are here, they're freely floating in that soup, in that plasma, which is very hot. Everything moves very fast. Temperature is kinetic energy, as you will remember. And what happens is that photons, they scatter of electrons. It's a particular scattering, I think, let me look at the handout. The general scattering phenomenon is called Compton scattering. And this is a special version of it. It's called Thomson scattering. You can follow a link in the handout if you want. So there is a critical temperature, we know the physics of it, below which these photons are not scattered anymore, because the electrons are then binding to the protons, forming hydrogen atom. And it's the same thing that happens in a star when you go away from the center and the temperature is just right, and then you get the photosphere. The light can come out. So that's the best way to explain this for us as being non-physicists. And we know that the temperature is fairly accurately from physics, what that temperature is, that critical temperature. And that refers to a recombination era, which is a misnomer. The word re should not, or the prefix re should not be there, as if electrons have been combined with protons before. That never happened in the history of the universe. This was the first time, combination era. I'll come back to the names they give for that. So this is the basics of this cosmic microwave background. So here you have a kind of a time diagram where it's also an idea of the whole universe around us everywhere. If you go back into history, there was a Big Bang, the start of the universe, extremely hot and dense. And there was a period which you go inwards to where we are, which is in the course of time, in the young universe, that the scattering was happening all the time. And then there was and this is a better word for it, called the surface of last scattering. And that is where the time in the history of the universe, when the universe became transparent and the light could come out. And that light that came out was basically infrared wavelength. And then because of the expansion of the universe, this wavelength has been lengthening, and you can calculate that if you have an idea about the age of the universe, that this would now be in the microwave range. And it would be observable in all directions. I have talked about cosmological redshift. That's the phenomenon which is causing this radiation, starting at infrared, to lengthen to what they estimate now to be something like 2 millimeter wavelengths. They're not estimating it anymore. They can observe it very accurately. So that's confirmed, which means that we have a measure for the cosmological redshift, which is basically the time that photons have been traveling. I discussed this a few lectures ago. But from galaxies and things, we have the spectral lines. We can create a spectrum, and we can see the redshift by finding those spectral lines. You can't do that with this because it's a diffuse radiation. They don't have spectral lines, so you cannot observe the redshift directly. But there's a fantastic feature on this radiation, which they predicted already in the very early days, that it would be a perfect black body radiation, as it's called. I'll come back to that. The very first conclusion from the discovery of this radiation was that those discussions between different groups, which I have explained, Fred Doyle was he was the guy who invented the term Big Bang. Remember, I mentioned it before. He had the steady state theory. They kept staying with that theory, which would explain the observed expansion, but which still would make the universe constant. That is the famous steady state theory. Finally, and this is in the 60s, this has been going on for decades, this discussion. Finally, that was now settled. There was no way, if you observe this radiation, that you could say that the universe had not started with a very dense and a very high temperature beginning. Basically, the Big Bang idea. So that was the first outcome from this discovery in the 1960s. And if you look at the idea of an expansion and the rate of expansion, then that's where cosmology comes in, of course. You can estimate that this temperature, this critical temperature that the universe became transparent, happened at something like 370,000 years after the Big Bang. if there would have been a uniform expansion over that time. So here's the black body radiation that I'm referred to. We talked about this, must have been in the Nature of Light lecture in the second course this year. A black body is an object that radiates electromagnetic radiation, gives off electromagnetic radiation, but only dependent on its own temperature. It doesn't reflect anything. That's basically what it does. It absorbs anything that's coming in, and it emits radiation which is purely dependent on the temperature. And Max Planck was one of the physicists who derived the mathematics for this. And I've shown you, when we talked about color, measuring peak colors of stars, that was the first way to estimate the temperature of a star, the photosphere, that we got these curves. And in general, this is the wavelength versus the intensity of the light that comes off a black body. You have a whole envelope of these kinds of curves. These curves go kind of down, but if you have longer wavelengths. But what happens, and the physics is completely clear about that, is that the peak of this curve, which is the intensity, the highest intensity, and if you look at what wavelength that is, that wavelength gives you a precise measure for the temperature of that black body. And they, because of the physics, even Ralph Archer and Hermann already knew that this should be a black body radiation, basically a perfect black body radiation. If you would observe this, that you would get such a peak, and then the peak will give you the temperature that it had at the time. No, that gives you the temperature at the current radiation when we receive that in our in our telescopes. I'll come back to the various programs that we have had to observe the radiation, but the latest value is that the temperature now, when we observe this radiation after traveling for some more than 13, maybe 13.5 billion years, the temperature is now defined to 4 decimals in degrees Kelvin, plus or minus 6 units in the 10 to the negative 4 figure. So this is an extremely precise measurement. Why? Because this is an extremely precise black body. The first satellite that, and I'll come back to that observed this radiation really all sky and in a systematic way was CMB, the Cosmic Background Explorer, or something it's called. And when they created this these data points here, the blocks, these are including error bars. This was world news. There were immediate publications. Absolutely exciting that this was the most perfect black body radiation that we had ever observed. So this definitely confirmed the origin of that radiation and the fact that it exactly follows the physics that we know about black body radiation. So in other words, we have a very accurate measure of the temperature of that radiation now. And there is physics about this, that if you know the temperature at the time that the light was emitted, and we know that from atomic physics, which is the temperature that electrons can bind with protons. So when the universe became transparent, that is a fairly well-known temperature from atomic physics, which is something like 2,970 degrees Kelvin, just around 3,000 Kelvin. And the physics of redshift is such that you can't measure it from spectral lines, but if you have those two temperatures, then the ratio between those two temperatures gives you the redshift. And the redshift that we can observe from this reasoning, first measuring the peak, which gives you the present temperature. Atomic physics gives us the temperature at the time that the universe became transparent, that originated the radiation. If you take the ratio, you get the redshift of that cosmic microwave background radiation. In the next few steps later, we will see that we can also measure the distance. And if you have combination of some sort of distance measure out of the whole list, I have had a lecture about various distances in an expanding universe. We can actually derive a specific distance for that radiation as well. And if you then combine the two, you have the whole story. To study the expansion of the universe over all that time. Just going back in general is about this radiation. The anisotropy, I've been studying the pronunciation of this. It's called anisotropy. Isotropic means, and I discussed this in the last week, this was one of the simplifications of the universe, the model of the universe, to make the field equations manageable, remember. Homogeneity of the universe means the same density everywhere. And isotropic means that in every direction where you look, you see the same thing. And anisotropy is the opposite of isotropic. It is non-isotropic. And that means these are these very small fluctuations in temperature that we can see. This is the color coding. I'll come back to that in those images of the cosmic microwave background. Those very tiny temperature differences, which is called the anisotropy in English, they are the origin for the formation of matter, which was getting more dense, and gravity took over, and then you got the formation of stars, galaxies, etc. So the fluctuations, which are extremely small in terms of temperature that we measure in the cosmic microwave background, they are the origin for the evolution and the formation of the universe as we know it now. If this wouldn't have happened, or if this radiation would have been completely smooth, we wouldn't be here. There would be just radiation. That's all. There would not be matter clumping into stars, etc. So this is a very, very, in a way, a dramatic conclusion about the early history of the universe, which is confirmed by this radiation. Let's look a little bit at observations, and then I'll go into the conclusions that cosmologies are deriving from this. CMB was the first satellite. There was another satellite in the Soviet era, which was only years later. There was one publication coming into the West. There was no communication very much in this Cold War era, and it was very minimal. But it was very clever. It was an attempt to have an observatory in space and telescope which could observe this microwave radiation just to confirm whether it was there. That was basically the whole idea. But it is a very important start. And then you had the NASA satellite CMB, was in 1989, sorry, which gave an all-sky image of the temperature differences in this radiation, in this image here. 20 years later, just over 20 years later, there was the Wilkinson microwave anisotropy probe. I think that was the reason of why they called it WMAP. Also launched by NASA, which gave in 2003 this result here in the graphics. And again, the color coding is minute differences in temperature. I'll come back to the magnitude of that. And then the latest satellite by the European Space Agency was Planck, launched in 2009. And the first results came out in 2013. And this is the current standard. It has been reanalyzed in further generations of results, but this is the latest standard, the Planck observations of the cosmic microwave background, with an amazing resolution and accuracy. And everything that we expect that we can do in cosmology with this radiation is coming totally true with from all the research that's been done with and still being done with this radiation, these observations. If we are sitting on a planet which rotates and that orbits around the sun, and the sun moves around the center of the Milky Way, and the Milky Way moves into space. So we have all those radial velocity components with respect to this radiation that comes in from the universe. And obviously we need to correct for all these motions. So we really need to do our best to find out what all these velocities are the Earth around the sun, the annual orbit, that's about 30 kilometers per second. I mentioned this before when we talked about the Milky Way probably. In the Milky Way, we move around the center with something like 220 kilometers a second. And then the Milky Way in the local group moves with something like 630 kilometers per second. These are figures that we need because this is the raw information we get. It's kind of a dipole because we have a very systematic motion with respect to the radiation that comes in. But if you do that subtraction, then they get this fantastic detailed temperature diagram, basically, of that radiation in an all-sky image. So it's in all directions. Here you see an idea about the range of the deviations from a median temperature. This is in this case, it's a half thousandths of a degree Kelvin, a millikelvin. Basically, the fluctuations that you see color-coded here are in the order of 10 to the negative 4 in temperature. So these are extremely small temperature variations. This is why you need very high resolution and amazing amazing technology to observe this radiation. Just a few comments about the various programs I mentioned. So this was the first experiment launched in '83. It observed this dipole effect, and it gave some upper limits for this the variations in temperature that they were expected to observe. And again, this was only based on reanalysis much later because in the West, nobody knew about this project in the 1980s. And then COBE is the Cosmic Background Explorer I mentioned. It still had limited resolution, as you remember from that graph, but it definitely found the anisotropy in the early universe throughout the whole sky in all directions. They saw these fluctuations. And this caused a Nobel Prize for Mather, what's his first name? Ralph Mather, I think. Mather. I mentioned him when we talked about the James Webb Telescope. He is the leader of the James Webb Telescope program. But before that, he was the leader of the COBE project. And especially when this extremely precise I was going to say black hole. This perfect black body radiation was observed. Then that got the attention of the international community, of the scientific community, big time, that he knew, okay, this really is real. And that's why the Nobel Committee gave Mather the Nobel Prize for that year. Must have been somewhere in the early 1990s. And then WMAP was the successor. It's launched at the L2 Lagrangian point, where the James Webb now is also, and there are several other telescopes there. It had 9 years of continuous operations. Now we have, from this, we got temperature variations to 1 part in 10 to the 5th, which is 10,000, no, 100,000. And a very good, much better angular resolution of 2/10 of a degree. It observed something that's called polarization. That's another, and I will mention it, but I'm not going into any detail. That's a physical explanation, that because of things that happened before the universe became transparent, there must have been some sort of vibrations that caused that cosmic microwave radiation, when it came out, to be polarized in a certain direction in a systematic way. That's something that's very, very much in the center of attention for the modern interpretation of this cosmic microwave background radiation. But it was the first time that this polarization was confirmed. And then you had the Planck satellite, which was launched in 2009. It was really the coldest spacecraft ever launched. It is colder than space itself, very close to absolute zero. In order to get the best possible resolution, they needed this radiometer to be cooled down to as close as possible to absolute zero. It has observed until 2013. And this was an order of magnitude more in terms of the temperature variations. And also the angular resolution was improved. This is just an animation of how the thing rotates in space and then systematically scans the whole sky. But you can do this for your watch this on YouTube. But it's fairly obvious. It also measures this polarization. And that's where we are going with this. We will see how this now feeds into the problem of cosmology. And in particular, what I mentioned last week at the end of the lecture is that we are now interested in the ratio between two density parameters, the matter density and the lambda density, or the cosmological constant density. And I'll give you a graph with the ratio of those two is plotted. And that's where we will go with the results of Planck. But that will be in the next lecture. So the significance really is that we have now 3 decades of observations with very much increasing resolution and also angular resolution, which means the fineness in an angular sense. Cosmology is now totally full-blown observational science because of this. As you will see, there's an enormous amount of information that comes out of this cosmic microwave background radiation. It was an immediate confirmation of the Big Bang model. The universe indeed started in a very dense and hot stage, a finite amount of time ago. So the universe has a finite age. And because of the temperature variations are so small, they're in the order of 10 to the negative 5, 100,000. This confirms that the early universe was very homogeneous. There weren't very many differences between different locations where this radiation comes from in terms of the temperature, which means that the early universe was indeed quite homogeneous, but definitely isotropic, because the anisotropic, and I'm struggling again, the anisotropy that they observe from this radiation, which is extremely small, 10 to the negative 5, confirms that the early universe is really very, or was very, very isotropic. And it probably still is now, and that's what cosmology is about. They're going to figure that out in the whole cosmological model using these observations. So this is really the a summary of the significance of this cosmic microwave background. There's a 15-minute video here. Actually, we have 12 minutes. I'll show you part of this, and then you can watch this at your own time for yourself. Let me just use that, spend a little bit of that time. I need to find the lecture or the video. CMB videos. I'll skip a bit of it.
Einstein showed that the speed would not be the speed of light plus 100.
He's interrupting me, or I'm interrupting him. He's talking about redshift and things like that. That's all basic stuff that you guys know. At some point, he starts to talk about the actual microwave background. So
right now,
Marvin is an interesting channel on YouTube. A lot of
imagine diving into a sea of milk and looking all around you. What would you see? Probably nothing but an opaque, featureless, uniform light all around you. This is analogous to the way the universe probably looked very early on for thousands of years, shortly after the Big Bang. And it was expanding throughout that time. Then, around 380,000 years after the Big Bang, a series of events took place that resulted in the universe changing from opaque to transparent. What caused this transition from initial opaqueness to transparency? Although there was a lot of energy and lots of photons were around, they were not free to move much. They bounced around and scattered. The reason is because the universe was so hot at that time that atoms were ionized. This means that electrons were not bound to protons. Both protons and electrons were moving around freely in a plasma state, somewhat like the way they are at the center of the sun. When electrons are free to wander around like this in the plasma, photons can't travel through them unimpeded. They interact with the electrons and scatter. This would prevent the light from one end of the universe to reach your eyes directly. It would be scattered randomly, so you would not be able to make out any features. However, after about 380,000 years, the universe cooled to about 3,000 Kelvin, or 2,700 degrees Celsius. This is still pretty hot, about twice as hot as liquid iron. But the universe now had a low enough energy such that electrons could combine with protons to form stable, neutral hydrogen and helium atoms. At this point, then, the universe became transparent because photons were now free to travel from one end of the universe to the other without being scattered by electrons. One thing you might be wondering is, why is this light from the very early universe microwave light, which is a relatively low energy light? Shouldn't this light be higher energy, like X-rays or gamma rays, since the early universe was extremely hot and energetic? Well, the answer is that indeed this light was higher energy or shorter wavelength originally, but at 2,700 degrees Celsius, it was not energetic enough to be X-rays or gamma rays. It was mostly in the infrared range. In fact, part of this light was also in the visible range, so you would have been able to see it with your own eyes if you were there. However, during the ensuing 13.7 billion years, the universe has expanded. As space expands, since the speed of light is constant, the wavelength of photons increases with this expansion. This results in lowering the energy of the photons. So while the original photons were more energetic, by the time the light reaches us billions of years later, it is of a lower frequency. It's now in the radio wave or microwave region. And these microwaves are coming from every point in the universe. It's like a subtle background glow. In fact, when measured, its intensity to frequency ratio fits perfectly over the graph for a black body. It's the most perfect black body ever measured. What does this mean? A black body is an object that absorbs all incoming electromagnetic radiation. In the ideal case, it absorbs light from any direction, in any frequency, and does not reflect anything back. Since it also absorbs all visible light, at room temperature it would appear to be perfectly black. That's where the name black body comes from. But black bodies also emit photons in the form of thermal radiation in a continuous spectrum according to their temperature. In fact, all objects above absolute zero emit some photons. This is called black body radiation. So black bodies above absolute zero not only absorb photons, but emit photons as well. Most objects are not perfect black bodies, so they generally don't absorb all the radiation. Objects tend to emit or absorb certain wavelengths of light more than other wavelengths. As it turns out, however, the CMB is possibly the closest we've come to observing a perfect black body. As you can see from the way its measured light fits on this ideal black body graph. The spectrum of photons emitted from black bodies looks different at different temperatures. When we measure the black body radiation from the CMB, we find that it matches the expected spectrum of an ideal black body for a very specific temperature. And that temperature is 2.726 Kelvin, which is about 2.7 degrees above absolute zero. So from examining the CMB, we can figure out exactly what temperature the universe's background radiation is. The fact that the black body spectrum is almost perfect suggests that the temperature is evenly distributed. And this means that the CMB is in a near perfect equilibrium, suggesting the universe was very isotropic and homogeneous when the CMB was formed. This means that the early universe was essentially the same in all locations and in all directions when the CMB was formed. This fact not only gives us a clue about what the early universe looked like shortly after its creation, but has profound implications for the way it looks today. The isotropy and homogeneity has manifested in a universe we see today where the average density of galaxies is the same throughout the universe and does not change much with distance or direction. You might ask, well, if the universe was the same everywhere at the beginning, then why are there any clumps at all? Why are there galaxies, solar systems, and even planets? Wouldn't the universe be perhaps nothing but a sea of radiation or a sea of atoms? Well, although the universe was pretty isotropic, it was not perfectly so. It has a small anisotropy. So this 2.7 Kelvin temperature of the microwave background is not perfectly uniform. It has a very small variation. The temperature of the CMB is more precisely 2.7 Kelvin plus or minus 0.00003, or a variation of about 1 in 100,000. And it's this deviation from being perfectly the same in every direction, the anisotropy, that led to the seeds which have grown to the large-scale structure of the universe we see today. It's mind-boggling if you think about it, but a region that was a fraction of a degree warmer became a vast galaxy cluster, hundreds of millions of light years across, containing trillions of stars. Where did this variation come from? The imperfections that led to the overall structure of the universe are believed to stem from quantum fluctuations in the early universe. The fluctuations led to the fact that some places had a very slightly higher matter density than other places. And over time, this led to certain places attracting more mass via gravity than other places. The structural formation within our universe ultimately comes from this process. Thus, the quantum fluctuations become the seeds leading to the structure in the universe as it expands. But it's still highly uniform. In fact, some of our earliest microwave instruments were not sensitive enough to detect such a minute temperature difference. The current temperature of the CMB comes from relatively recent advanced satellite data. But the fact that the CMB is almost perfectly isotropic also gives us a clue about how the universe was probably formed. It is evidence for the theory of cosmic inflation in the very early universe. Cosmic inflation is the theory that the early universe, from only about 10 to the negative 36 seconds after the Big Bang to about 10 to the negative 33 seconds, expanded exponentially from an infinitesimal point to about the size of perhaps a large orange. And following this, the universe continued to expand, but at a much slower rate. Many physicists believe that such an inflationary epoch in the universe explains the isotropy, because it would have stretched out space very fast. This would even out any significant imperfections, leaving only the small imperfections due to quantum fluctuations. And these quantum fluctuations, magnified to cosmic scales, became the seeds like the galaxies and the galaxy cluster formations of today. The CMB also reveals that the universe is probably flat. When I say flat, I don't mean flat like a pancake. What I mean is flat in 4 dimensions, meaning there is no overall curvature to our 3D spacetime. 2 parallel beams of light will remain in parallel forever. They will not converge or diverge. For example, if the universe was like a 4D sphere.
I'm stopping here because he's going into where I'm going with the next lecture. The conclusions that we draw about from these cosmic microwave background, but also other observations that relate to those density parameters that I ended my lecture with last week. So he was kind of running ahead of what I was going to say, but this is a very good summary of what he gave of the cosmic microwave background. The tiny temperature fluctuations that we observe, 1 in 100,000, extremely small. And in quantum mechanics, there is an explanation for that, that these were what they call quantum fluctuations in the very early universe that gave rise to these tiny little temperature, but also density variations in this very early stage of the universe. And those tiny deviations from isotropic, which is the anisotropy, that gave then rise, when the universe was cooling down and expanding further, to actual densities of matter, which then started to form stars, etc. That's where we will go. And he also mentioned other aspects of the inflation theory, for instance. I'll come back to that in the last lecture, because we have many open questions still, and the so-called inflation theory is an answer to several of those questions, a potential answer. But that's the topic for the last lecture next week. So anyway, we have summarized now the cosmic microwave background radiation and its importance for cosmology. And in the next lecture, which I will start after the break, this is perfect timing, it's 8 o'clock now, I will talk about various observations and what they mean for the various density parameters that we have defined for the universe in our model.